Hello students, welcome to EPG Pathshala. I am Dr. Nidhi Handa from Gurukul Kangli Vishwavidyalaya Haridwar. Today we are going to talk on module Discrete Probability Distribution and Poisson distribution under the paper Quantitative Techniques for Management Decisions. After completing this module, you should be able to understand the introduction, then Poisson probability distribution is what, different conditions, how to apply Poisson probability distribution, then different approaches to the formula for Poisson probability. Then problems are also discussed. The Poisson probability distribution, named after the French mathematician Simon D. Poisson. Poisson, this is another important probability distribution of a discrete random variable that has a large number of applications. Suppose a washing machine in a laundromat breaks down an average of 3 times a month. We may want to find the probability of exactly 2 breakdowns during the next month. This is an example of Poisson probability distribution problem. Each breakdown is called an occurrence in Poisson probability distribution terminology. The Poisson probability distribution is applied to the experiments with random and independent occurrences. There will be n and r occurrences will be used. Further, you will see the occurrences are random in the sense that they do not follow any pattern and hence they are unpredictable. Independence of occurrences means that one occurrence or non-occurrence or failure of an event does not influence the successive occurrences or non-occurrences of that event. The occurrences are always considered with respect to an interval. In the example of washing machine, the interval represents 1 month. The interval may be a time interval, a space interval, or a volume interval. The actual number of occurrences with an interval is random and independent. So, random and independent, very important terms in this probability Poisson distribution. If the average number of occurrences for a given interval is known, then by using the Poisson probability distribution, we can compute the probability of a certain number of occurrences x in that interval. Note that the number of actual occurrences in an interval is denoted by x. Now, condition to apply Poisson probability distribution. The following 3 conditions must be satisfied to apply Poisson probability distribution. Number 1, x is discrete random variable. Number 2, the occurrences are random. Number 3, the occurrences are independent. The following are a few examples of discrete random variable for which the occurrences are random and independent. Hence, there are examples to which the Poisson probability distribution can be applied. Consider the number of patients arriving at the emergency ward of a hospital during a 1-hour interval. A 1-hour interval is very important. In this example, an occurrence is the arrival of a patient at emergency ward. The interval is 1 hour and occurrences are random. The total number of patients who may arrive at this emergency ward during a 1-hour interval may be 0, 1, 2, 3, 4 and so on. The independence of occurrences in this example means that a patient arrives individually and the arrival of any 2 or more patients is not related, independent. Second, consider the number of defective items in the next 100 items manufactured on a machine. In this case, the interval is a volume interval, 100 times. The occurrences, that is number of defective items, are random because they may be 0, 1, 2, 3 up to 100 defective items in 100 items. We can assume the occurrence of defective items to be independent of one another. Third is, consider the number of defects in a 5-foot long iron rod. The interval in this example is a space interval. The occurrences are random because they may be any number of defects in a 5-foot iron rod. We can assume that these defects are independent of one another. The following example also qualify for the application of Poisson probability distribution. Number 1, the number of accidents that occur on a given highway during a 1-week period. The number of customers coming to a grocery store during a 1-hour interval. The number of television sets sold at a department store during a given week. On the other hand, consider the arrival of patients at a physician's office. These arrivals will be non-random if the patients have to make appointments to see the doctor. The arrival of commercial airplanes at an airport is non-random because all planes are scheduled to arrive at certain times, and airport authorities know the exact number of arrivals for any period, although this number may change slightly because of the late or early arrivals and cancellations. The Poisson probability distribution cannot be applied to these examples. In the Poisson probability distribution terminology, the average number of occurrences in an interval is denoted by lambda. The actual number of occurrences in the interval is denoted by x. The using of Poisson probability distribution, we find the probability of x occurrences during an interval given the mean occurrences are lambda during that interval. Poisson probability distributions formula. Now let us see what is the formula for it, and this is very important to be remembered. According to Poisson probability distribution, the probability of x occurrences in an interval is lambda raised to power x e raised to power minus lambda upon x factorial, where lambda is the mean number of occurrences in that interval and value of e is approximately 2.71828. The mean number of occurrences in an interval denoted by lambda is called the parameter of the Poisson probability distribution or Poisson parameter. As is obvious from Poisson probability distribution formula, we find to know only the value of lambda to compute the probability of any given value of x. We can read the value of e for given lambda from table also. Let us take one example. A washing machine in a laundromat breaks down an average of 3 times per month. Using Poisson probability distribution formula, find the probability that during the next month this machine will have exactly 2 breakdowns, at the most 1 breakdown. Solution: let lambda be the mean number of breakdowns per month and x be the total number of breakdowns observed during the next month for this machine. Then lambda is equal. The probability that exactly 2 breakdowns will be observed during the next month is probability that x takes value 2. So lambda raised to power x e raised to power minus lambda upon x factorial is equal, because value of lambda is 3. So 3 and value of x is 2. E raised to power minus lambda, that is e raised to power minus 3 upon 2 factorial. So after calculating the answer, have the probability. B. The probability that at the most one breakdown will be observed during the next month is given by the sum of probabilities of 0 and 1 breakdown. This will be written as probability that at the most one breakdown, that is 0 or 1 breakdown. So probability that x takes 0 value plus probability that x takes 1 value, and write down the formula. Take x is equal 0, then lambda is same in both the cases. Here x is equal 1 and lambda is same, and calculate the probabilities and add up the two. So one important point to remember about Poisson probability distribution is that intervals for lambda and x must be equal. Sometimes we come across several situations in which probability of an event is very small but the number of trials n is very large. That the event occurs several times, as can be seen from the following cases. The number of typographical errors by an expert typist in typing the manuscript of a book is fairly high. Then individually being born blind is a rare event and hence its probability is very small, but the number of persons born blind in a big city in a year is quite high. The probability of a person suffering from a disease such as blood cancer is very small, but in a big city in a year, the number of persons suffering from disease is sufficiently high. Thus, clearly, Poisson distribution is a limiting case of binomial distribution when P or Q is very small and N is large, so that the average number of successes, that is NP, is finite. In binomial distribution, the probability of R successes is given by B in bracket R comma N comma P. That is binomial distribution with R and P parameters. This is equal to NCR P raised to power R, and limiting case NP becomes M, that is mean. Mean and variance. If X is a Poisson variate, that is X follows P Poisson distribution with lambda variate, then mu is equal mean is equal expectation of X, and variance is sigma square, which is already discussed, is equal expectation X minus mu whole square. That is also expressed as expectation of X square minus mu whole square. So expectation of X square is M square plus M, and mu is M, so mu square is equal M square. M square and M square cancels out, so result is M. So variance is M and mean is also M in Poisson distribution. Mean and variance are same. Note, the mean number of occurrences in an arrival denoted by lambda is called the parameter of Poisson distribution or Poisson parameter. Now another approach to Poisson distribution. Let the random variable x denote the number of telephone calls during time t at a telephone switchboard. We assume that the calls are independent, number 1. Number 2, lambda denotes the mean arrival rate of telephone calls per second. Further, there are some more examples. For example, number of buses reaching bus depot in time t, number of suicides in a city in a year, number of persons joining a queue at a counter in time t. So here lambda is mean. In another example, experience shows that a box of 450 components of a company has 1% defective components. Find the probability that such a box has number 1 no defective, number 2 1 component defective, and number 3 at most 3 components defective. E raised to power minus 4 is given. Let selection of a component from a box be regarded as a trial and getting a defective component as the success. If P denotes the probability of success, then P is equal 1 upon 100, that is 0.01, which is small, very small. As the number of trials n is equal, 400 is large. So problem can be solved by Poisson distribution. The parameter m is equal n into p. Multiply 400 by 0.01. Required Poisson distribution. First probability that 0 defective. So probability that x takes 0 value is equal e raised to power minus m, and solve it. Then second probability that no compound, that one component is defective. So probability x takes value 1, and solve this for e raised to power minus m, m raised to power r upon r factorial, and have the answer. Third is at most 3 components defective. So at the most 3 components defective means ki 3 or less than it. So probability that x takes 0 value plus probability x takes 1 plus probability x takes 2 plus probability x takes 3. In this way, summation we have used and solve the probability using the formula for Poisson probability distribution. Next example, if the probability of a bad reaction from certain resin is 0.001, determine the probability that 1 of 2000 individuals, number 1 none, number 2 1, or number 3 more than 1, last is more than 2, and fifth is exactly 3 will get a bad reaction when exponential value of e raised to power minus 2 is given. So e raised to power minus lambda, that means lambda is equal 2. Let getting a bad reaction be regarded as success, then P is given. The selection of an individual being regarded as a trial, then the number of trials n is equal 2000. Hence the parameter of Poisson distribution, which is m, is equal 2000 into 0.001 is equal to. So it was also, hint was already given in the question also, that e raised to power minus 2. That means e raised to power minus lambda. That was mean. So probability that r are successes, formula is e raised to power minus 2, 2 raised to power r upon r factorial. First probability we will found that 0 success is there. So r is 0, which is 1. 0 factorial is 1. So e raised to power minus 2 is the answer. Probability that 1 success. So again in the denominator, r factorial means 1 factorial, and 2 raised to power r means 2 raised to power 1. So 2 times e raised to power minus 2 is the answer. Now probability more than 1 success. That means probability of 2 successes plus probability of 3 successes plus probability of 4 successes, and so on, since n is 2000. So up to 2000 we have to add. So what we will do is that we will subtract it, summation of all, and we will subtract it from 1. So 1 minus probability that 0 success minus probability of 1 success. This will be 1 minus e raised to power minus 2 minus 2 e raised to power minus 2. That is the answer. You can solve it. Next, probability that more than 2 successes. So probability that 3 successes plus 4 successes plus 5 successes, and so on. Again subtract it from 1. So 1 minus probability that 0 success minus probability that 1 success minus probability 2 success. So probability of 3 success plus probability of 4 success plus so on up to 2000 successes is equal to 1 minus probability of 0 success minus probability of 1 success minus probability of 2 successes. And in this way you will solve and have the answer. Now probability of 3 successes, only 3 successes. So e raised to power minus lambda, lambda raised to power m upon m factorial, or e raised to power minus m, m raised to power r or upon r factorial. So solve it and have the answer. Now next example, the probability of getting no misprint is e raised to power minus 2. Find the probability that a page contains more than 2 errors. The required Poisson distribution is probability that there are r errors is equal e raised to power minus 2 into 2 raised to power r upon r factorial. So probability that there are no error, that means r is equal 0, so e raised to power minus m, and then probability that there are 2 errors or more than 2. So this will be written as probability that 2 errors plus probability that 3 errors and plus so on. So what we will do, that subtract it from 1. So sum of all the probabilities and subtract it from 1 and have the answer. So this is the question. Next, a manufacturer of cotter pins knows 5% of this product is defective. If he sells cotter pins in boxes of 100 and guarantees that not more than 10 pins will be defective, what is the probability that a box will fail to meet the guaranteed quality? Thus, the number of trials here is 100. Again, it is large in number. The probability that a cotter pin is defective, that is probability of success, is P is equal 5 upon 100. So n into P is equal lambda. Parameter for a Poisson distribution m is equal n into P. So this is 100 multiplied by 5 upon 100, which is equal to 5. Probability of R successes is e raised to power minus m, that is minus 5, 5 raised to power r upon r factorial, and probability more than 10 defective will be 1 minus summation r takes value 0 to 10 and e raised to power minus 5, 5 raised to power r upon r factorial. This is the answer of the question. Suppose the number of telephone calls an operator received from 8:30 am to 8:40 am. Follow Poisson distribution with mean 2. Find the probability that the operator will receive number 1 no call, number 2 1 call in that time interval tomorrow. Exponential value is given. Poisson distribution has mean m is equal to, hence the required Poisson distribution is probability number 1 that no calls has been received is probability that r is equal 0. Second is probability that 1 call is received, so probability that r takes 1 value, and solve it with the formula. An auto salesperson sells an average of 9 cars per day. Let x be the number of cars sold by his salesperson on any given day. Using Poisson probability distribution table, write the probability distribution of x. Let lambda be the number of cars sold per day by the salesman. Lambda is equal 0.9. Using the portion of corresponding to lambda is equal 0.9, we write the probability distribution of x in table. So note that 6 is the largest value of x for lambda is equal 0.9 listed in the table, for which the probability is greater than 0. However, this does not mean that this salesperson cannot sell more than 6 cars on a given day. What this means is that probability of selling 7 or more cars is very small. Actually, the probability of x is equal 7 for lambda is equal 0.9 calculated by using Poisson formula is 0.00039. When rounded to 4 decimal places, this probability is 0 as listed in table 1. So this is also one type of problem in this Poisson distribution. So students, let us summarize what we have learned in this module. If the average number of occurrences for a given interval is known, then by using Poisson probability distribution, we can compute the probability of a certain number of occurrences R in that interval. Here total number of occurrences is n, and probability, because probability is very small, note that the number of actual occurrences in an interval is denoted by R. The average occurrences during an interval for a Poisson distribution is its parameter, very important point. In this distribution, the number of occurrences is large and probability is very small. So mean and variance, here mean and variance are also discussed, their distribution function is discussed, and related problems are also solved. Thank you.